Three.
Hello, and welcome to today's T&D World webinar titled Upgrade Your Aging Infrastructure with Modular, Sustainable, and Hardened Switchgear, sponsored by PDI Squared and ABB. I'm Jeff Postlewaite, Managing Editor of T&D World with Endeavor Business Media. So just to get us kicked off with today's presentation, if you've got any technical difficulties during the presentation, just submit your questions below and our technical experts will help you out. We recommend that you turn off any of your Chrome plugins or pop-up blockers, extensions in your browser, because these can cause some problems with the player sometimes. And we really, really do welcome your questions during today's event. That's the fun part about these is the questions that come in. So, send those in to us during the Q. You don't have to wait for the Q&A session. You can send them in at any time just using the question window and hitting submit. And also today's session will be recorded and will be available at our website at tndworld.com within 24 hours, and we'll notify you by email when that's available. I'm going to hand it over to our moderator for this webinar, Mr. Mike Beeler.
Thank you very much, Jeff. I appreciate that, and welcome everybody to today's webinar with ABB. We're really excited to talk about hardening your equipment. I just posted something the other day on LinkedIn that talked about our industry, and we're going to spend, according to this article in the Wall Street Journal, $165 billion in 2024 and 2025. It's the highest number that EEI, the Edison Electric Institute, has ever recorded in the history of EEI, $165 billion. So if you're going to do that, how are you going to do it? And ABB is going to talk about that today when we talk about upgrading your equipment and making it modular, configurable, and adaptable. It's going to be a fascinating conversation. It's brought to you by the Power Delivery Intelligence Initiative. PDI Squared is a group of contractors and consultants and equipment manufacturers and vendors that advocate for looking at the total cost of ownership of an asset over the life of the asset. We are in the underground industry, so we want planners and engineers and now data scientists to look at the total cost of ownership of overhead versus underground. And we're bringing these webinars to you because we think they make a lot of sense. ABB is part of the board of the Power Delivery Intelligence Initiative, and we're really excited to have them today. And from ABB is Abe Shockett. Abe, give us a quick hello.
Hello, everyone. Hi, Mike. Thanks for the introduction. I'm really excited to be here today and looking forward to the discussion.
Abe has got a bunch of really interesting things to share with us today, so buckle your seatbelts and send your questions in like Jeff asked, and we'll try to get to them at the end, and we might interject one or two as we go. But Abe Shockett from ABB, take it away.
Okay, thanks. So here's our agenda for today's discussion. I'm going to cover a little bit about history and some of the building blocks that come together to make up the switchgear. And then we'll jump into a range of case studies about different conversions, replacing existing gear for a variety of reasons. I did want to point out at the beginning that this presentation is in no way a critique of any other technology or any other insulation system for switching, other than customers replace gear for all kinds of reasons, including my own company's gear, and we'll go through some of that. So we'll talk a little bit about the reasons behind these things, and then you'll see how they come together. So first, the history. You probably are familiar with rubber molded goods, elbows. Elastomol's been molding product for 60-ish years. The first elbow that is on record is this non-load break 200 amp connection in a street lamp pole from 1963 in Somerset West. Somewhere in New Jersey, I think. I'm up here in New Jersey myself, and I tried to find this pole but couldn't. And when I Google Somerset West, it turns out it's a resort in South Africa, apparently. So I'm not sure that's where this pole is either, but I've kind of lost track of this location. The interesting thing about elbows and rubber goods is they have evolved significantly over the years. And it really wasn't until the 70s that the IEEE started to think about standardization of what these products look like. And now, because of standards efforts, which is a combination of work by the utilities and the manufacturers, we do have quite a bit of uniformity, interchangeability, dependability, and reliability. So standards are good efforts for us all to be involved in so we can coordinate and reduce costs for everybody. So in addition to the elbows, rubber molded products, I want to talk about vacuum switching, because vacuum bottles inside molded rubber is how our switchgear works in the solid dielectric switchgear. So vacuum bottle history, you can see goes back almost 100 years to Caltech. GE bought the patent rights, but really nothing much happened for a number of decades, probably because of the Depression and then wars. But it was in the 50s when we started to see product at the medium voltage level that could actually switch and be an effective solution. Then you can see as we go through the 60s and 70s, we start to see more applications in switchgear. And then into the 80s, replacement for SF6, gradually in some applications, medium voltage. And then finally, 2018, capability reached all the way up to 145 kV, 200 Ka. So bottle technology has evolved quite a bit. The main components inside the vacuum bottle are pretty uniform across the manufacturers, but there's quite a bit of differentiating technology in the contacts, because when the contacts open and the arc is formed, it has to be extinguished. Different shapes of contacts, different metals can actually manipulate the arc to move it apart, to concentrate it, to split it, to allow it to be extinguished more effectively. So there's some examples in the center of different types of technology, and depending on the manufacturer, you will get differences in what those contacts look like, even though from the outside, of course, it looks more like the bottle on the right picture where you just see the housing. Another interesting thing about the contacts and the mechanism in a vacuum bottle is the bellows. The bellows is the part that moves up and down because it's inside a vacuum and you can't risk any kind of leak. So only one of the poles moves, the other one's stationary, and the actual movement is just compressing the bellows, which allows the contacts to open. And vacuum bottle manufacturing is in a clean room environment. These are examples from the ABB factory. There's a mix of manual and automated equipment, and there is vacuum chambers, and there are quite a wide range of sizes and shapes now to handle all kinds of different levels of power. So finally, I show this vacuum plus EPDM technology chart where we compare line to ground separation for a 35 kV, 150 kV BIL example. And you can see that vacuum and EPDM rubber are down on the left at the smallest separation, which makes it a nice choice for an effective compact package for medium voltage switching. Air being the biggest distance required, no surprise there, but air has been an effective insulator ever since electricity was invented. The nice thing about air as an insulation choice is it's free, and if without it, we wouldn't have all the overhead distribution we have today, and transmission for that matter. So moving on to the switchgear.
Abe, let me just interject. That was a great start. And one of the things one of the comments you made was about standards. And between now and the top of the hour, I'd love to hear your comments about standardization. And do you see us in the industry starting to improve our standards, upgrade our standards? We've got all these challenging things that we want to do with distributed energy resources and electrification. Are you seeing standards improving to accommodate the new technologies, or do a lot of companies still rest on standards from the 60s and 70s and 80s? You can comment on that as we go, if you would, please.
Yeah, sure, thanks. So I've been involved in a few different efforts to write standards, mainly efforts to upgrade standards, because standards have a defined life and there's a defined process for improving them over time in the IEEE. So most standards will be in the process of either revision or voting or launch, and then it starts all over again. So they're kind of, in that way, they're kind of like live documents. Not all standards, but the main ones that govern the high volume gear, the cables, cable accessories, switching and protection equipment are always moving forward. So I think, you see the collaboration between the manufacturers and the users in these meetings. Usually it's, 10-to-1 manufacturers to utilities. So I encourage utility people to participate. It helps drive, it drives the standard forward, but it also helps identify things that are wrong with the standards. So there's always a lot of questions about, well, why is this in the standard, or where did that come from? And who remembers, how do we harmonize between this standard and one that's related or one that's in Europe? So I would say that in general, it's a forward-moving progress for sure.
Yeah, excellent answer. Thank you very much.
So I'm showing a picture of solid-dielectric switchgear. Just a couple of points about switchgear. It's dead front, so it's fully shielded, and there's no live parts when you open the doors. Even though utility crews typically have specific safety operating practices that govern how they interact with equipment, whether it's live front or dead front. So we don't drive that, but we do facilitate some ease of that because it's dead front. So all the load and fault current interruption is in vacuum. There's no oil or gas or air to manage or worry about. Compact, lightweight, fits in tight spaces. One of the key features about solid dielectric gear is it's modular, so you can take components out, move them around. It gives us flexibility of how we create gear to fit existing installations for replacement, which is the key point of this presentation. So this modularity and reconfigurable features helps us to accommodate customers who have specific cable positions, specific bushing heights, for example, and size restrictions on the pads. So moving along, some of these modular components, the main ones are switches and interrupters, and you can see what the ratings are typically here. This is 15 through 38 kV gear, 95 up to 150 kV BIL, 600 amp. Spring mechanisms. There are also features like motor drives or mag actuators that will give us different performance. And then the standards again, this probably should say IEEE and C3774 and 60. These are both standards that are currently being worked on for upgrading and will be going to ballot in the not too distant future. And here's a cutaway of what the switch and the interrupter look like. You can see there's a, the red parts show the current path through the bushings. The bushings are standard IEEE 386 interfaces, so you can plug a T-body, 600 amp T-bodies directly onto both sides with the bottle, the vacuum switch in between inside the rubber. There's a pole that operates this, which is enabled by the handle or by a spring mechanism and a trip coil on the left for the interrupter. There's a small purple block in the center of the left picture, which represents the current transformer. So the current transformer is monitoring the current through that bushing. And then depending on how the customer programs its trip settings, it'll initiate a trip when that threshold is exceeded. And here's a few pictures. There's a pad mount configuration on the left, riser pole, which is kind of an overhead underground transition consideration in the center, and then modular in a vault, so rack-mounted gear instead of in a pad mount enclosure. And
a quick question here from a utility. I'll just throw it in here real quick, Abe. Utility wants to know, can these vacuum interrupters and switches be fused?
So these are not fused. the devices I showed, the interrupter is programmable to replicate a fuse. So you can pick from standard industry fuse curves. I'll show one in a minute. You also have the capability to manipulate the shape of the curve and some other characteristics around curve delay. So it acts as a fuse, but it's not a fuse. So it's resettable without having to replace any parts. There are molded rubber devices with fuses inside them that act as a fuse link that have these standard IEEE 386 interfaces and with a removable fuse in our cable accessory range. So something like that might be used in conjunction with switchgear sometimes. I'm showing what's called the True Break module. This is a mechanism that is attached to the front of the switch, and then it has interlocks with the switch, so you can physically open and see through the center window that the contacts are open. So this gives you a visual disconnect. So I should say many utilities require visual indication that the contacts are open before their crews are allowed to physically disconnect anything, pull cables, work on the equipment. So visible break can be achieved through this kind of a modular solution also. There's a little close-up of the window. Also, in solid-dielectric switchgear, you need controls to, like we talked about, programming interrupters for curves. This type of switchgear works with our own Elastomold brand of controls, but also interfaces with other industry standard controls. I'm showing some Schweitzer control relays here. There's a 751 or 751A. It's quite common for controlling one of the ways, and this one on the right under auto transfer is, I think it's the 451. And then the equivalent Elastomold product faceplate shown on the right. So there's quite a range of control options. And the fuse curve I talked about, you can pick up, here's an E standard fuse, you can select this in the control, but you can also manipulate these curve shapes to some degree. Okay, so now we'll get into some examples of these conversions. The first one is air-insulated switchgear to solid-dielectric. Air-insulated switchgear has been around for a long time. It has a very successful history in the field, and it works great in many environments. But for some reasons, different reasons for different utilities and in different environments, sometimes they have chosen to want to replace this. This type of gear uses, obviously, air for the insulation. The fault current interruption is usually with fuses, and you need spares for the fuses. And because there's air, there could be something bridging the gaps across phase to phase or phase to ground if critters can get in. If there's corrosion, if there's high humidity, these things can reduce the insulating characteristics. But in general, there's quite a bit of air-insulated gear. It's typically the lowest first cost option, and it's perfectly adequate for many applications. There's also a dead front version of air-insulated switchgear. Here's a picture where there's a panel in front of the live front component so that when you open the door, you're not facing exposed bus and terminations. There's also some mechanical handle mechanisms here that allow you to open up the fuse connection and pull that out and replace it all with hot sticks. So in this particular air-insulated retrofit project, the customer requested to replace it with dead front solid-dielectric switchgear. There was an existing pad, cables, and conduit already in place, so there was a requirement to line everything up, including ABC to CBA phasing, so that's an additional challenge here, along with the height of the existing cables required that the bushings match a certain height requirement. And there were some additional drivers in the project, wanted to move to a dead front, wanted to avoid the possibility of switching flashover issues they had seen in the past and move to vacuum and solid dielectric, avoid fuses and spares, more control over the fuse curve settings, and coordinate through the control with SCADA for FLISR applications. So here's just some photographs showing before and after. The upper left is the existing gear, and then as we go around, you'll see on the right at the top, the existing gear has been removed from the pad, but the cables are sticking up. And then the new gear in the bottom left is lowered directly on top of the existing pad. And then in the right bottom, you'll see it looks like a nice fit. I can show in the next slide one side before and after. So the cables were live front terminations, so those were cut and then terminated with elbows that were then plugged in the on the bushings in the solid dielectric gear on the right side. And then this is the back side of the gear. You can see on the air insulated side where the fuses are, and then on the right side again the elbows plugged into the single phase interrupters on that side. Then we get to,
I'll interject a question here real quick from the audience. Big utility out west. Is there a gauge or do you have alarms for your vacuum switchgear when the vacuum has been compromised?
No. So there's no vacuum monitoring in this gear. We don't have a history of problems in this space where that would appear to be needed. Long life has been proven out so far, so that hasn't been an issue.
Good, thank you.
In the four-way job, here we see the single phase. Each way had 3 single phase interrupters, which had to be spaced quite far apart in order to match up with these cable locations. So that's why it looks so spread out, but that's because they were already spread out on the existing phase, again with ABC CBA phasing. In this engineering drawing, the black dots represent the existing locations for cables that had to be matched. And this is a couple of source ways on the top and the three single phase each on the load ways on the bottom. And then we show here that in order to figure out how to make the spacing work, the utility actually mocked up in their shop floor plans on this wood platform with where the cables are and the conduit openings in order to make sure the gear was going to fit. And then you get to the job site picture on the right where the old gear has been removed, and you can see these cables sticking up out of the pad. They really can't be moved. So it's not an open pit of any kind. It's just fixed concrete locations, and then the cables can be cut and re-terminated with shielded elbows. Here's another view, source side re-terminated, and on the right, the load side. I showed that picture at the beginning with the spread. So again, it just points to with modular components, with cable bus, with bus jumpers, with different kinds of parts in our toolbox, I would say it gives us the flexibility to match existing locations in what would otherwise be difficult to accomplish without having to dig out the pad or splice in new cables. Another example of modularity, this solution here, the customer wanted to go from a live front to a dead front application. So you can see in the top right, these gray live front terminations connected to the incoming bus, and then the cable runs down into a 600 amp elbow, so it's a shielded dead front connection. And then there's the vacuum bottles are inside the rubber behind these metallic brackets, and then you have the outgoing cables at the bottom, also dead front 600 amp cables, T-bodies. Another application here is there was a large lineup. It's a 6-way with space for future growth. So you can see in this application, the individual ways are connected with rigid bus jumpers across the top of the gear. There's also two PTs to power the controls, shown there in the upper left, where the PT is also completely submersible, dead front, and uses a 200 amp elbow to tap primary power going into the PT, and then you get 120 volt out of the secondary. This is automatic transfer scheme, so you need a PT on each side for each source. So if you lose power on one side and you're switching, you still have power to run the controls on the secondary source. And here's another picture of the gear. It's too big to fit in one picture, so I split it. But you can see on the left picture, on the right side of the left picture, is the space that's to accommodate a future way. So it's just active ports that are capped off there for another three-phase connection. And then on the right, you can see the fully loaded side of three of the ways.
Hey, Abe, I got a couple of questions in here for you before you leave this topic.
Right.
And would you answer for this civil engineer, please? When you say completely submersible, are you talking about the capability of being completely underwater?
Yeah, the gear is designed to be submersible. The spec that it meets is 3 meters for, now it's slipping my mind, 10 days. 3 meters, 10 days. So something on the order of that. It's not designed to be put in the bottom of a lake and left there.
Right.
But if you're in a flood zone and you have intermittent issues, tides and storms and things, then you can handle all of that. Also, we put the vault gear directly into vaults that submerge regularly, daily, with tides, all kinds of issues with water, and don't see any problems. We have a 10-foot cylindrical tank out back here at the R&D Center where we drop gear in and verify its watertight performance.
Yeah, one of the concerns about underground electric is that, oh, well, what happens when you have a storm surge or something like that? And having worked at Hawaiian Electric Company, we have an awful lot of stuff underwater a lot of the time. So anyway, I just wanted to clarify that. I do have a question here from a big West Coast IOU. As a four-way, do these single-phase operate as a gang-operated switch?
They can, yes.
Okay.
So there's also a gang modification handle that can lock them together, or they have individuals and can be handled separately. So either way.
Good. Okay, let's go ahead and move on. Thank you for answering that.
Yeah, and just another point about submersion, the ferocity of storms over the last few years seems to be increasing. We have a utility customer that required 10 feet for quite a while, and then after a hurricane descended, they needed 25 feet. So, it's getting a little harsher all over the place, I would say. So now I want to talk about oil to solid-dielectric conversions. Oil switchgear requires monitoring and maintaining. Filling is an environmental concern. The interruption is under oil normally. So there are some risks. Again, oil insulated gear has been around a long time with a very successful history, but all things that are aged can get to end of life and need excessive amount of maintenance. So that could drive utilities to replace on different schedules, depending on what their asset management schemes look like. There was a notice about, I blocked out the names, but it's representative of the fact that the dielectric strength of the oil insulation can go down if excessive moisture gets in. So this was an industry announcement that is on the internet, so it's publicly available. But just a point about insulation materials do change their characteristics if they're not in an environment where they were originally designed. And also there's an issue with, as part of this advisory, that the metallic enclosure can be damaged or rust or end up allowing moisture into it in ways that aren't predicted. So it's something to be concerned about. This is a particular piece of gear that the customer wanted to replace. Again, it was a ABC CBA phase requirement to maintain, no new cable, and it had to fit the existing pad. So when this unit was pulled off, there was some, you can see here, well, I don't know if you can see it, there's some cable bus across the middle here from the left way to the right way. So it allowed us to make that phase jump from ABC to CBA. We had to build a custom support frame to get the bushing heights to end up in the right places so that the existing cables could be used as is. Another utility did have an issue where old gear failed and had to be replaced. This was excessive moisture in the oil, and the gear failed violently. And then the new gear matching the pad exactly, and you can see the existing, in this case, the existing cables are coming out of a pit. So there's quite a bit of flexibility for moving them over and up and down a little bit. There's, you don't have to be as rigid about the locations. And when the replacement unit came in, you can see in this case, it's 5-way double-sided. There's an empty way on the other side that on this side you can see 3 ways, and on the other side there's space for future. And then finally, in very old gear in a vault where they were using these live knife switches, I've seen this kind of stuff very rarely, but occasionally you'll still run into equipment rooms or vaults with really old gear that needed to be replaced. There's a barrier board on the bottom right to block off and provide some safety. And in this case, we put in a couple of vault gear racks that are modular and allow you to connect them at whatever spacing you need to accommodate the cables in and out. Now on to SF6, unless there's a question. Okay, so SF6 has been, again, another insulation material that's been around a long time, very successful. It's used extensively in substation breakers. Unfortunately, it's a greenhouse gas, and some states are moving to eliminate it or minimize its use in new installations. There are a number of issues around SF6 byproducts if there's arcing in SF6. Sometimes it's difficult to configure in small spaces for multi-way configurations. It's becoming more regulated, so this drives some utilities to have a program to want to consider replacement. So as an example, in California, CARB issued final regulation order of Title 17 that requires, and you can see it's based on voltage capacity, so less than 38 kV above ground for all short circuit ratings has to be phased out by January 1 of 2025. So I've talked to some utilities about not this particular CARB requirement, but the general pressure to eliminate SF6 equipment. And because it's still the dominant material in a lot of equipment, particularly at higher voltages and substations, maybe the distribution people see a little more pressure to do something than the substation guys do. Anyway, this is a piece of SF6 gear that the customer wanted to replace. And again, you can see, I don't know if you can see it, but there's a pit that the cables come out of. So there's a bit of room to move things around, which makes it a little easier. There's a better picture showing the pit after the gear's been removed. This is a low-profile, single-sided piece of gear that the customer was very concerned about replacing in the same footprint to avoid putting something in that was bigger or more obtrusive, or where they had to do a lot of rework on the pad and the cables. So here's the new gear dropped into place. Again, it didn't require a different pad, it fit right on it, and the cables could be accommodated directly without having to cut and splice in sections. In this case, we used bus jumpers across the back of the gear in order to keep the thing as low in height as possible, but still interconnect all the ways.
So Abe, you and I, before we went live, we talked about lead times for various products. If somebody's got a deadline of January 1st of 2025, when should they start getting this done? It sounds like with long lead times, this could be very challenging.
Well, clearly, if you need to buy some switchgear from anybody today and you want it delivered by January 1, depending on the configuration, it could be quite challenging because the industry is still, I would say, pretty constrained. I see everything from 30-ish weeks up to a year and longer. So, yeah, it's time to get out of planning and into purchasing.
Yeah.
So here's a vault where some SF6 gear needed replacing due to age, and they wanted to add some sectionalizing capability in the gear that they didn't have. So they had to get the gear out through this constrained space and get new gear in. It had to be submersible because the vault is routinely flooded. And in this case, there's a picture showing the new gear, a rack-mounted vault frame with a single three-phase switch on it being lowered down through the hole. There's plenty of room in there. You can lower these things and then put them together once you're down inside the vault. So here's the final installation with those three ways that were each frame was lowered through the hole one at a time, and then they get bolted to the wall with the appropriate spacing and then bussed. You can see the feeding cables at the bottom capped off, ready for final installation. And it looks like a bunch of connecting plugs just sitting on the top up there. Somebody stuck those there. Anyway, so that's the kind of installation you can do in a vault as an example. Another vault job, this vault looks a lot cleaner. And this was in California, so there was nothing wrong with the gear, but as part of the CARB requirement, they were starting to replace equipment. And this is, again, lowering the frames down one at a time and then interconnecting them with cable bus across the bottom and rigid bus across the top. Ways interconnected at the top and cables in and out at the bottom. Also, I have a couple of slides here. You know, I think I mentioned it at the beginning. Even our own gear gets replaced. All gear reaches end of life, or customers need different features or different capabilities. This was a case where the switchgear was fully operational. It had been subjected to salt spray, saltwater hurricanes, high tides down in the southeast, and they wanted to add new features to the gear. So because of a lot of these issues, they decided to replace the gear. And you can see here that I guess the point here is you really want to be aware of what kind of environment you're putting your gear in. If you want stainless steel, you want stainless steel enclosure, but you also want stainless steel frames and hardware inside, as opposed to maybe galvanized on the inside, stainless on the outside. So, you know, think about your environment and spec it appropriately. And in this case, the gear was pulled out and replaced here with some brand new gear that fit directly on the pad and matched up nicely with the old, out with the old and with the new. So that's my main presentation about the different applications for retrofitting in different situations with different kinds of gear for different reasons. I did want to make another couple of comments about undergrounding in general, and particularly because we are, as it was mentioned by Mike at the beginning, we're members of PDI Squared, and PDI Squared produced a document about a guide to undergrounding. There are quite a few documents out there, and in fact, this document is a nice quick summary that's kind of a myth-buster document about why things are not what you might think when you're starting to plan and trying to exercise some cost thinking about how to do undergrounding for certain strategic circuits. And in the reference to this guide, there are many deeper articles about what's been done and examples. So I encourage anyone who's thinking about undergrounding or starting to think about how do I get started planning, what are the cost concerns, how do I take the long view, for example, and get support. That's in this guide. So that can be made available also. So that's all I have to say. I can turn it back over to Mike. We can talk about questions if we have, I think we have some time left.
We do. Thank you. You covered a lot of material there, Abe, in a short amount of time. So thank you very much. And thanks for that reference to the guide that at PDI Squared. So the Power Delivery Intelligence Initiative tries to be a resource for planners and engineers and data scientists as they are looking at the total cost of ownership. And yeah, I think you'll find PDI2.org is a rich resource. So thank you for mentioning that. We got some questions from the audience. Go ahead and send in some more, but let me go to, I might work from the most recent ones backwards a little bit here, but based on these installations, you were showing all these pad-mounted switchgear and such, and this question is, are these installations resistant to vehicle damage and bullets? So what about the physical ability of these cabinets to withstand impacts, I guess is a good way to say it.
There is an IEEE standard for enclosures for pad mounts, and I don't remember seeing anything in there about testing for bullets or trucks or cars. But I have seen pictures of what happens when a car runs into a pad mount, and unfortunately it's not pretty for the pad mount or the car. So I can only say that a standard, I think it's 12 gauge steel pad mount, is not going to withstand car impact or bullets. I have heard stories about people shooting at equipment, particularly in substations, and the kind of damage that can be done. So I don't think any of the standard enclosures we're talking about for this equipment or electrical equipment in general is really designed for that.
I would agree. And I've seen some car hit poles where a couple concrete poles for the car, literally down here in Florida, the car was split in two. The car hit at a very, very high rate of speed and split in two, and the concrete pole stood right there. Okay, enough of that. Another public power utility out west. Could you explain how much work is involved in assembling the solid dielectric bus work in the vault?
Yeah, it's actually quite simple. If it's rigid bus and the frames are bolted up correctly with the right spacing, they come with spacers that kind of forces you to position these things correctly, then it's as simple as it would be installing a 600 amp T-body on each bushing. So the bus bushing to bushing is quite simple. And if you're in a different kind of configuration where you have to put the things further apart and jumper with cables, again, it's just standard shielded power cable with 600 amp T-bodies with normal installation practices, because all the bushings on the gear are either 600 amp bushings or 200 amp wells.
Okay, got another question from a big public power utility out west in the Mountain West. What's the interrupting rating of the 15 kV MVI?
Interrupting, if we're talking short circuit currents here, then the standard is 12.5 kA for 15, 27, and 38 kV gear. The interrupting rating is a function mainly of the bottle, the vacuum bottle, and there are other ratings available. I know in this industry there are different available fault currents based on how dense, how close you are to the substation or the generators. Particularly these days with distributed energy resources, we hear a lot of requirements for 25 kA, wind farms, 38 kV with 25 kA, data centers. So there's all kinds of, I would say, growing difficult requirements, and different manufacturers make solid dielectric switchgear that can accommodate different ratings. I do admit that my own ratings chart has some holes in it. You know, I can't hit every rating at every voltage, but in general, it is something to discuss with your supplier upfront because it does might drive some requirements around space and availability of the gear. If you're talking about steady state current, load current, these are all 600 amp or 630 amp. Sometimes customers ask for 800 or 900 amp. If you're a cable and cable accessory guy and the cable accessory person will say, well, if you use copper lugs and copper cable, you can run this at 900 amps. So if you're running 900 amp cable and cable accessories into your 600 amp gear, there's a throttle there. So I think gear under certain circumstances has been and can be rated to 800, maybe even 9 for other manufacturers.
That's a great candid answer. I appreciate that, Abe. Here's one. Have you anything to replace 27.6 kV SF6 switchgear where the fault levels exceed 12.5 Ka? Sounds like a pretty specific question. Maybe you should get your manufacturer's rep over there, but
yeah,
I'd say you could answer that, but I would like to go back and revisit this SF6 a little bit more too. Maybe you can expand on that in the couple of minutes that we have here.
So that was the second question, Mike?
So well, just in general, I like the topic of SF6 gas replacement, but this one is replace the 27.6 kV SF6 switchgear where fault levels exceed 12.5 Ka.
Yeah, I think SF6 gear, oftentimes I see specs from customers that says, here's what my current spec is. Can you meet this with your gear? And it's going to say 25 Ka for the fault current, and we often can't meet that, particularly at 27 point, whatever this question said, 27.6. So gear can be, we do have configurations that could be tested to meet higher levels. We do have a 25 Ka 38 kV interrupter, and we have a version that is 40 Ka at 27 kV as a switch. So the switches and the interrupters are different, and they have different requirements. One is what can the device withstand, and the other is what can the device make and break, open and close into a fault. So an interrupter has a much more severe requirement, and it's easier to withstand high fault currents through switches. But normally a configuration of switchgear is going to have switches on the source side and interrupters on the load side. Not always. Sometimes it's all switches or all interrupters. But there's no point in having gear where only some of the devices meet a certain level if they're all bussed together, because your weak link is going to be the place where it fails. I also will say it's when you have a standard or a utility practice that says, hey, I have to meet 20 Ka or I have to meet whatever you have to meet, and that's the way it's always been, it's difficult to go back and do the studies and confirm what the short circuit current available really is. Sometimes it's not 25 Ka. Sometimes it's 20, sometimes it's 16. Sometimes if you're a mile from the substation, it drops off dramatically. So these things can allow you to differentiate it, which gear selection you make.
Okay, that's a great answer. Thank you. And that goes back to standards. And you gave a wonderful answer about industry standards, but sometimes utilities have their own standards around which they make decisions for speccing various equipment. So comment on those utility standards, and then answer this question that was one of the very first questions that came in today. Talk about the need for doing transient studies while using vacuum switches or vacuum interrupters.
I can say, utility standards never say, meet IEEE C3774 and what year, and that's all it says. It's always a multi-page document that has a lot of special considerations that are required for that utility. Everybody's got different environment, different practices. So we always review these things in great detail here and provide design drawings for approval before we bother to build any gear. So I think it's not surprising that the standard for the utility is quite an adaptation beyond what's in the industry spec. So like I said, the industry spec from IEEE is a collaboration of competitors, manufacturers, and users.
Right.
And it's I don't want to call it the lowest common denominator because these are very stringent and difficult to pass production and qualification testing. So they're not weak, but they do accommodate, a lot of different variety under a single line or two in testing sometimes. Right. So the utility opportunity to elaborate for the specific needs and requirements of their operation as well as electrical requirements. As far as detailed transient studies, this is not something I've seen or know how to do. It might require a PE with some expertise or a consultant. We might have people in our company, but this isn't something we've no one has to do. So I can't really comment on that piece.
Okay. I have one last question here from a big IOU in New York, and it's back to the single-phase interrupter question and the need for fusing or some fuse-like device. So here's the question. So the single-phase interrupters can be programmed to simulate a fuse individually, but for three-phase switching, do you need a controller?
So I would say you can do what you want either way because a single-phase interrupter has a circuit board in it that you can program directly and pick a fuse curve. And then a three-phase unit will have a single point of interface for programming if it's internal control. So there's also a single curve characteristic for all three phases in that case. So three-phase versus single-phase, either way.
Okay.
You need control, but you don't need external control. So for example, the devices have built-in control, or you can port out to an external control, and the external control could be simple, like the kind we make, bare bones, or it could be sophisticated, like a Schweitzer relay or Beckwith or somebody else, GE, ABB even.
Okay, so during this conversation, Abe, we talked about, you mentioned renewables and data centers. Are there other non-utility types of customers that are coming to you now that are trying to connect utility scale or developer-driven renewable sites, whether it be wind or solar or plus storage, or are there data centers that are coming in and saying, hey, we're going to build our own connection to maybe our own solar farm or our own solar plus storage, et cetera, et cetera. So are you seeing beyond the traditional utility, regulated utility, municipal or cooperative utility, are you seeing new kinds of customers that are coming to ABB?
Yes, for sure. So the C&I market is also expanding and building new factories and requiring large pieces of switchgear. They operate their own substations, but particularly data centers and wind farms, solar farms. These things are representing huge loads and demand on the utilities. I was at a conference not too long ago where the utility participants were speaking and talking about how the planning departments are being overwhelmed with requests for interconnection for data centers where the amount of power requested is so high that it's like nothing they've ever seen, and the growth rates that they're projecting if they accommodate these data centers will be the highest since air conditioning, which is, as you can imagine, when air conditioning first came out, that was like the reason to get electricity probably. So, we see it from both sides. We see large factories. Even our own company is building large factories and asking us to provide gear for it. And then we see utilities saying, we have these requirements. We talk directly to the large, the FANGs, the companies that are building the data centers. They have their own engineers designing the distribution systems now. And these are quite onerous in terms of load and short circuit capability. And I think we'll just see more of that as time goes by over the short term for sure.
That's interesting. We actually had some architects that were listening into the webinar today, and so they are probably the ones that are involved in developing these things. And it's interesting that you say that you're dealing with engineering resources that are not from utilities or even from traditional AEC firms, that they work directly for the Amazons and the Googles and the Microsofts of the world. Is that true? Is that what you just said?
That is what I said. And, I think the biggest companies in the world are these companies that we all know by name that I don't mention here, but they do operate quite vertically sometimes, in terms of wanting to control everything. So, and control the design. So I'm not surprised that we get contact from these people. We actually have so much contact that I think our biz dev department decided to put people, 100% on these market segments.
Yeah, that actually makes a lot of sense. So, Abe, I got to give you a minute here to wrap up and give some concluding remarks, but we started off by saying that the industry is going to spend $165 billion this year and in 2025, and EEI says that is the highest amount of capital spend in the history of the Edison Electric Institute. So what an exciting time. It sounds like you've got, all sorts of interesting products and services to provide to the industry, and now you're providing them to people that are building, huge loads, whether they're factories or whether they're data centers or connecting to large utility scale renewables. Give us some concluding thoughts as we prepare to sign off today.
Thanks, Mike. So I do feel like this is a time like no other in this industry. I've been in and out of electric power for a long time, and we always used to project our forecast based on GDP plus a couple percent if we were better. And now it's like, well in excess, and has been for a while, and the supply chains are constricted everywhere. Getting a little better, but it really requires a lot of planning to be able to get design and keep your design from changing by the time the gear and all the other related equipment shows up. So it's a different time for most of us in this industry about how we work, and there are just so many different kinds of opportunities out there for related to undergrounding, for grid hardening, for resilience, these DA schemes with more sensors, higher accuracy sensors. All these things are make it a really interesting time in our industry, and I'm just happy to be a part of it.
Yeah, likewise, it's fun to be part of it. Last webinar we did, Abe, was on the Champaign-Hudson transmission project that is this massive transmission project that's basically delivering power from Canada down into the New York City area. Today we talked about the distribution system and the challenges that we have ahead of us in a massive build-out that we're going to do. So it is a really exciting time. I'd just like to say on behalf of the Power Delivery Intelligence Initiative, thanks for listening in today. We are really excited about the future, and we encourage you to look at the total cost of ownership over the life of the asset as you make considerations of whether you're going to go overhead or underground. So with that, thank you to Abe Shockett from ABB, and Jeff, back to you at T&D World Magazine.
Thank you, Mike. Yes, that is all the time that we have for today. But for those for those questions that we didn't have any time to answer, we'll be getting back to you via email. And that's it for today. So on behalf of T&D World, I want to thank our speaker for his presentation. Thank you, Mike. Thank you to PDI Square and ABB for sponsoring us, and of course for all of you for joining. I hope you have a great rest of your day. Thank you.